Everyone, welcome to this video on the terminal velocity lesson, lesson 14 of the forces and space scheme of work. And this is like a classic GCSE question. I'm not even sure they ask it very much anymore in the new spec, but I still think it's just a really good lesson to teach students because the level of conceptual thinking that's required to really answer this well is quite deep. You need to really get the link between velocity and drag force, the effect of changing drag force on resultant force, the effect of a change in resultant force on acceleration, and therefore the consequent effect on velocity, and you kind of go in this cycle. So writing this is just a really good exercise for students to really get to grips with their understanding of these core concepts that we've been addressing in this scheme of work, basically Newton's first and second law, and that's why it's in here. So the way I like to teach this is to draw diagrams, and the way I lay out these diagrams is designed to support students' thinking. So if we lay out the diagrams in a really precise, clear order, then students can effectively turn those pictures into words. And I'll also show how I would model the writing of this, because it's an explain question, and how we would use causal language. And hopefully you'll see how the layout of the diagram supports the order in which it's written. I apologize, this might be a bit of a longer video because I'm going to draw a diagram and do some writing, but hopefully it will be worthwhile for you and your students. So always start with the concrete. So I like to, the first example in the slides is about the parachutist, or the skydiver. It's a classic example. So I like to start with a picture of an aeroplane like this. So we can draw an aeroplane like this. And I quite often get students to draw with me, so they've got something to refer to in their book. And what we're going to do is trace the skydiver's journey from the moment they jump out of the aeroplane as they fall through the sky. So in the first instance, I'm going to draw the parachutist like this, about here, just as they've jumped out of the aeroplane, like that. And what we want students to recognise is that at that moment the parachutist jumps. We're going to look at this in more detail, I think, in the next lesson on vertical motion, but just at that moment that the parachutist jumps, their velocity, or their speed, is approximately equal to 0. They're not really moving, they're pretty much stationary, but they're going to start accelerating. This is what we saw in Galileo's experiment. So at this point, the velocity is small. Now, if we sketch the forces on this skydiver, so let's sketch some forces here. And this is where I would tell students this, or I might call someone to just check they remember, but this is going to be the weight. I'm just going to label that as W to save time here. And again, going back to the lesson that we did on drag forces, it's very similar scenario. Hopefully they recognise that if the velocity is small, I'd ask them, show me in your thumbs, do you think the drag is going to be big or is it going to be small? Hopefully they'd all show me it's going to be small. So we've got a very small, very tiny drag force here. Now I'm not going to put numbers here, although I could do, well, yeah, do you know what? Maybe it's easier if we put some numbers in. So let's say the weight is 700 and the drag is going to be, I don't know, 50 newtons. So they've not really got going yet. Very tiny drag force. So if I was to calculate the resultant force, we always need to set our direction as positive. So I'm going to put downwards as positive because the parachutist is moving downwards. So that seems like a sensible way to do it. So my resultant force, I'll just put this as F equals, is going to be plus 700, because that's in the downwards direction, minus 50 newtons, because that is going in the opposite direction, 650 newtons. So again, I'm modelling every single lesson, or most lessons, I'm modelling this process so that students are just in these habits. So I've got a resultant force of 650 newtons downwards, quite a large resultant force. And if I've got a large resultant force, again, I might ask students, show me your thumbs, is the acceleration going to be big or small? Hopefully they recognise it's going to be big. So I'm going to put a large acceleration here. I'll put accelerates rapidly. So then I can say, well, okay, imagine 10 seconds later, my velocity is going to have increased. It doesn't really matter what units you do here. You could do miles per hour like in the last lesson on speed, or you could do it in meters per second. I'll do it in, I think, meters per second, let's say. So let's say my velocity has gone up to 10 meters per second. Parachutist is now here. Skydiver. Doesn't really matter what we call them. So now let's think about the forces. Hopefully the students will recognise that the weight hasn't changed, so that's still going to be 700. And again, you're going to ask questions, whole class response, what's happened to the drag force. You want students to recognise that if the speed is increased, then the drag must also have increased. So now this drag force is going to be a bit bigger. Let's say the drag is equal to 500 newtons. So if I then calculate my resultant force, I'm going to have plus 700 minus 500, which is equal to plus 200 newtons. So that means there is still a resultant force downwards. It's just not as big as it was before. So I've got 651 here. This is only 200 newtons. But that means it's still accelerating. And again, just as we saw in the lesson on drag forces, we don't want students to think because the drag's increased it starts slowing down. It's still accelerating, just less rapidly. So let's put accelerates less rapidly. So then that's another good opportunity to check for students' understanding. We can think, well, okay, 10 seconds later, what might the speed be? Now, if students start telling you 8 meters per second or something, the fact that it's slowed down, then they've clearly not realized that it's still accelerating, just not as quickly as before. What you would hope is that they would spot that it's not going to be 20 meters per second if it's the same amount of time. Actually, it's going to be a bit less. So let's say v equals, I don't know, 12 meters per second. And thinking about it, this is going to be accelerating at a similar rate to gravity, isn't it? So the gravitational field strength. So the numbers are going to be a lot higher than this. But anyway, we don't need to worry too much. This is just a sketch. So what I'm going to do now is draw the parachutist having fallen a bit further. Draw my forces. Again, you want to elicit the idea that weight has stayed the same. So that's still going to be 700 newtons or whatever it is. But in this case, now at this point, the drag has kept increasing until it's also 700 newtons. And this shouldn't be new because in the drag forces lesson we looked at something very similar. We can do the resultant force calculation, so we get plus 700 newtons minus 700 newtons. And they should be able to spot anyway that the forces are balanced and therefore this resultant force is 0. So that means there is no resultant force. So we don't need to draw an arrow. If you want to emphasize the point, you could draw a dot or something like this to show that there's no resultant force here. And therefore there's no acceleration. So we could draw a dot there as well, if that would help. And what that means is, now, if I move my camera down, the skydiver is traveling at a constant speed. And hopefully, this should be relatively familiar. Really, the only new thing we're going to say here is this constant speed of 12 meters per second, that is what's called the terminal velocity. And I find it sometimes quite helpful to then draw just one more stage of the story, another 10 seconds later, and ask students, firstly, what do you think the velocity is going to be? And secondly, what forces are acting? So hopefully they should recognise that the velocity is still going to be 12 meters per second if we're using our made up numbers, and the forces acting should still be our weight of 700 and our drag 700. Now obviously it gets more complicated when the parachutist opens their parachute, but we're not going to go into that. But what I want to point out to students is that this figure, this top speed, it just keeps going, and if we just draw another picture, it would still be 12 meters per second, and so on and so forth. This is called the terminal velocity. I might pause this video, or stop this video here, and then I might do a second video on how to model the academic writing, just so the videos aren't too long. So there will be another video to follow.